This is the introduction to section 1.8, which is continuity. So I have start here with four functions graphed for you. And I want to talk a little bit about what's different about each of these functions. So if we look at the first graph here, the function f of x is x squared minus 3. And what can we say about that function? Well, it has no holes, it has no gaps in it. Everything, you can trace that function by starting in one spot and never having to pick your pen up off of that function, right? Of course, it goes off to infinity, so I can't do it for the entire graph, but you can see the idea. And so we say this function f of x is continuous. We'll talk about what that means more formally mathematically in a minute. The second function does have a break. In fact, it has a vertical asymptote here at x equals 2. So the line x equals 2 is a vertical asymptote. And so we say that g of x has an infinite discontinuity at x equals 2. Anytime we have a vertical asymptote, that vertical asymptote is going to give an infinite discontinuity. Other ways that functions cannot behave like x squared minus 3, and they can be discontinuous. Here's a function we saw in the introduction to the first section of the quarter, I believe, x squared minus 4 divided by x minus 2. Maybe it was divided by x plus 2, but either way, when we graph this function, it looks a lot like the line x plus 2, but h of x is not defined at 2, so there's a hole in the graph there at x equals 2. So this would be the point 2, 4. And we say that h of x has a removable discontinuity at x equals 2. We say removable because we only have to redefine one point to make that function continuous. If we defined with input 2 to have output 4, we would fill in that little hole and the function would be continuous. Hence why it's called a removable discontinuity. Okay, the last function looks like 3 when x is greater than or equal to 2, and looks like -1 when x is less than 2. And we see here this gap where we jump from -1 up to 3, and j of x is said to have a jump discontinuity at x equals 2. Okay, so we have a continuous function, we have a function with an infinite discontinuity, and we have a removable discontinuity and a jump discontinuity. Now, anywhere that we don't have a discontinuity, these functions would be continuous. So for example, j of x is continuous on the interval from -infinity to 2 and on the interval from 2 to infinity. And anywhere on that interval, we could find the limit. If we want to know the limit as x approaches 5 of j of x, we would just evaluate the function at 5. If we wanted to find the limit as x approaches 0 of j of x, we would just evaluate the function at 0. We'd use the direct substitution property from section 1.6 to find those limits. And when you can use the direct substitution property, that would implies then that the function is continuous at that point. So here it is. A function is continuous at an interior point of its domain if the limit as x approaches a of f of x is just f of a. So this is the limit definition of continuity. This will come up probably a few times, so this is a good definition to have down. Basically, it says if we can use the direct substitution property, then the function is continuous. Okay, so let's look at another function here. This function f of x is the square root of 9 minus x squared. What can we say about its continuity? Well, let's see. Before we answer that question, what can we say about its domain? It takes as inputs anything between -3 and 3, including -3 and 3. So that's the closed bracket another way to say this is negative 3 is less than or equal to x is less than 3. Those are equivalent statements. That's the domain of this function. We see no jumps, gaps, no jumps, removable discontinuities, or infinite discontinuities. So it's continuous. Well, it seems, I'm not certain about the endpoints. So it's continuous from negative 3 to 3, not including negative 3 and 3. So that's negative 3 less than x less than 3 is what that notation means. And what do we say about those endpoints? Well, let's think about one of them. Let's think about x equals 3. So here's 3. And what can we say about the limit as x approaches 3 from the left of our function? Well, if we're coming in towards 3 from the left, the function is decreasing and getting closer and closer to 0. What can we say about the limit as x approaches 3 from the right of f of x? Well, the function isn't defined to the right of 3. There are no inputs out there, so this limit does not exist. And so because these two things occur, we say f of x is left continuous at x equals 3. Similar analysis on the other side at negative 3. As we approach this way, the limit would be 0. So as we approach from the right, the limit would be 0. As we approach from the left, the limit does not exist. So f of x is right continuous at x equals negative 3. Okay, so it's continuous on the open interval from negative 3 to 3. We say it's left continuous at 3 and right continuous at negative 3 because of the limits that exist. All right, so what is a continuous function? If I just said to you I have a function that is continuous, what does that mean? That means that it's continuous at everywhere within its domain. Another way to say that is I can find the limit of that function using direct substitution all of the time. Okay, so what are examples of some such functions? Well, if you picture any linear function, like y equals 6x minus 4, you can always directly substitute to find the limit, and that function is going to be continuous everywhere. So in general, anything that looks like y equals mx plus b, we can generalize lines pretty easily. Polynomials. So any polynomial function, any nth degree polynomial function, in fact. So I don't know, we'll write a couple down. Let's see, for example, f of x equals x cubed minus 6x squared plus 3, or g of x equals x to the 11th minus 10x to the 6th plus 4. Those are functions that are continuous everywhere. Rational functions. Rational functions are continuous everywhere if one very important thing does not happen. So let's say we had a function that looks like this. X cubed minus 1 divided by x squared plus 1. There's an example that's continuous everywhere, and it's because the denominator is not equal to 0. So it's key here that x squared plus 1 is never equal to 0. So rational functions will be continuous everywhere if their denominator is never equal to 0. If their denominator is equal to 0, that rational function will have a discontinuity, and that discontinuity will either be an infinite discontinuity, or if some factoring can be done, it will be a removable discontinuity. Okay, some trigonometric functions are continuous everywhere. The two that we're most familiar with that are continuous everywhere are sine of x and cosine of x. Okay, we have one more idea that's related to continuity, and so let's see if we can get that down, and then I'll have you take a look at the activity related to section 1.8. So here's a question. Here's a graph of the function x cubed minus 1. And I want to know if we can guarantee that it takes on the output 17 divided by 10. Okay, 1710, that's 1 and 7/10. So I guess that's somewhere maybe right around here. And if we just look at the picture, which this one's easy to graph, we could see that somewhere, yes, it does take on that output of 17/10. How would we find that input? Well, we would take x cubed minus 1 and set it equal to 17/10. We would get x cubed equals 27/10, and so x is the cube root of 27 over 10. Okay, that's great. We can do that easily with a function x cubed minus 1, but we may not have functions that are so nice to work with algebraically. So let's look at one other way we could think about this. This function, f of x equals x cubed minus 1, what do we know about it? It's continuous everywhere. It's a polynomial. We just decided polynomials are continuous everywhere. So this is one of those functions. Clearly, let's see, it takes on the output of 0. Sorry about that. F of 1 is equal to 1 cubed minus 1, or 0. Let's see, what happens at 2? F of 2 is 2 cubed minus 1, or 7. Okay, it's continuous. It goes through the point 1, 0 and the point 2, 7. Sorry, my email is, let me close that so we don't hear it keep dinging. It goes through the point 1, 0 and 2, 7. It takes on the output 0, it takes on the output 7, and you can't pick up your pen if you're drawing it. So it must, because it's continuous everywhere, must take on all outputs between 0 and 7, and hence 17/10. Okay, let me try to illustrate this slightly more generally. This is what we call the intermediate value theorem. It says if a function is continuous on a closed interval from a to b. Okay, let's just start with unpacking that statement. So I'm going to draw some closed interval from a to b, and we're going to have some function that is continuous on that interval. Okay, so we have a function, it's continuous on a closed interval. Let's change colors here. If n lives between f of a and f of b. Okay, so let's see, we go there. So if we come across to the x-axis, there would be f of a. If we come up and over to the y-axis, about right here is the output of the function at b. And if n lives between those two things, so here's some value n that lives between f of a and f of b, then there exists some value c that lives between a and b, where the output of the function at c is equal to n. How would we find that value c? We'd draw a horizontal line at n. We'd see where that hits the function. We'd go down to the x-axis, and there is our point c. It lives between a and b, and the output of the function f of c is n. Okay, this is the intermediate value theorem. I'm not going to prove this one for you. I may prove slightly fewer things this quarter than normal. This is one that we'll just illustrate with this picture. Okay, the question is though, how can we put that intermediate value theorem into practice? All right, here's a question. How can we use the intermediate value theorem to show that x cubed minus x minus 1 has a root somewhere in the interval from 1 to 2? Okay, well, what do we know about this function f of x? It is a polynomial. In fact, it's a third degree polynomial. It doesn't matter. We know it is continuous everywhere. Which means if it's continuous everywhere, it's definitely also continuous on the closed interval from 1 to 2. Okay, so let's see. We have the beginning of the intermediate value theorem. F of x is continuous on a, b. In this case, a and b are 1 and 2. So we want to know, what is f of a? F of 1 is 1 cubed minus 1, or negative 1. Okay, f of b. Oops. F of b, but b is being played by 2, is 2 cubed minus 2. I can do this. 2 cubed minus 2 minus 1, which is 8 minus 2, which is 6 minus 1 is 5. Okay, well, what do we want to show? We want to show that f of x has a root. So that means we want to show that f of something is equal to 0. Well, where does 0 live? It lives right in here between negative 1 and 5. So since negative 1 is less than 0 is less than 5, the intermediate value theorem says there exists some c in the interval from 1 to 2 such that f of c is equal to 0. It's challenging to find that c algebraically. I would probably need a computer algebra system, but I can just use the intermediate value theorem to show that it exists. So what does that mean? We know somewhere between 1 and 2, this function must cross the x-axis, right? We just showed that at 1, the output of the function is negative 1, and at 2, the output of the function is 5. And so the only way I can connect those points with a curve is if I cross the x-axis here somewhere, and f of c is equal to 0. Okay, so go ahead and use that information about continuity and see if you can work through the activity that's posted related to section 1.8.